last singularity function which we will talk about is the unit delta function or unit impulse function. It is also called unit delta function. Also referred as Dirac delta function because it was introduced by Dirac. Now, one can introduce this in this fashion. Suppose I have a symmetrically situated pulse, symmetrically situated around the origin of width d and height 1 over d. So, this pulse has a width d and a height 1 over d. And now, let us imagine what happens when d is reduced to by a factor 2, then the pulse width diminishes, but the height increases, so that the area under the curve is 1. So, the area is equal to 1. So, maintaining that area, you have to make, as you make d smaller and smaller, then the pulse width becomes smaller, but the height grows, so that the area under the curve is maintained equal to 1, and this is d by 2, this is minus d by 2, and it is still centered around the origin. So, imagine what happens when d goes to 0. When d goes to 0, you should have ideally a pulse which has got 0 width, but a height which is infinitely large. So, that is what is called the impulse function or delta function, which is indicated because we can't mark the point at infinity in a blackboard or in your notebook. We will indicate an arrow like this and say this is 1, indicating that the area under this curve is equal to 1, and this is called delta t. This function is called delta t. So, delta t is, we can define it in this manner: limit as d goes to 0 of this symmetrically situated pulse of width d and height 1 over d. That is one way of defining this delta function. You can also think of, start with other waveforms like triangle waveform and take the limit and it goes to 1. That is also possible, but we will confine our discussion to this. A second way of defining delta t mathematically would be to say delta t equals 0 for t not equal to 0. So, this is 0 for every value of t except t equals 0. At t equals 0, it has infinite height, but we do not know how to describe this. So, all we can say is, if you integrate delta t from an interval a b such that 0 is in between a and b, that means the range of integration includes that delta, this is equal to 1. That means the area under this curve, this infinitely large amplitude 0 width curve, is said to be equal to 1, and therefore, as you integrate through the origin, integral from a to b of delta t dt equal to 1. So, that is one way of defining this. A third way of looking at this delta function is this: delta t equals 0 for t not equal to 0 as before, but suppose you take a function f of t, multiply by delta t and integrate from a to b. Then what do you have? You have this delta function multiplying a function f of t. So, you have a continuous function, let us say f of t is a continuous function, and then you are having this delta function. When you multiply these, it is 0 everywhere except at this point. At this point f of t is multiplied by delta t. So, f 0 this value, f 0 is this value is multiplying this delta t, and the integral delta t dt is equal to 1. All we have now is instead of delta t dt you have f 0 delta t dt, therefore, this is equal to f 0. So, this is another way of looking at a delta function. Any continuous function f of t, if you multiply by delta t and integrate, it samples that value of f of t at the point where the delta is situated. Delta is situated at t equals 0. So, you want to find out the value of the function f of t at t equals 0, you multiply f of t delta t dt, integrate, you get f of t. So, these are all equivalent ways of looking at this delta function. We can adopt this as the definition. Sometimes you can even use this as a definition, or you can take this as a definition. All are equivalent ways of looking at this. Important thing is that this delta function is something, again, as I mentioned, which may not be which is not coming under the fold of the classical mathematics. So, originally when it was introduced by applied mathematicians and engineers, and later on mathematicians established a theory called theory of distributions, which makes the manipulation of delta functions, puts it on a more sound basis of rigorous mathematics, and therefore, we do not go into the theory of distributions, but there is a branch of mathematics called theory of distributions, which gives a theoretical basis to the use and manipulation of delta functions. Okay. So, let me now plot some examples of how different types of delta functions can be conceived. Suppose I have 4 delta t. It is an impulse function standing at t equals 0 and its magnitude is 4. I mean, we indicate its magnitude 4 in the sense that it's no doubt infinity, but the area under the curve is 4 units. So, the magnitude of a delta is indicated within brackets in this fashion. Suppose I have 3 delta t minus 2. It means the magnitude of this delta function is 3, but it is now sitting at t equals 2, because whenever the argument of the delta is 0, then only delta exists, otherwise it is 0. That means this will be t equals 2 and its magnitude is 3. That is how 3 delta t minus 2 looks like. Suppose you have minus 3 delta t plus 4. It means that at t equals minus 4, that is the position where delta is fixed, and its value equals minus 3. Therefore, it is a negative going impulse with a magnitude of minus 3. That is how it goes. A few further properties. Delta t equals delta of minus t. It is an even function of time. So, delta t exists at t equals 0, delta minus t also exists at t equals 0 and nothing else. Therefore, whether it is plus 0 or minus 0, it makes no difference. Therefore, this is an even function of time. Secondly, delta t multiplied by f of t equals f 0 multiplied by delta t, because f of t multiplied by delta t is 0 for all values of t except t equals 0. So, the value, if at all it exists only at t equals 0, at that time f 0 times delta t is the value that we have. Thirdly, if I integrate delta t minus t naught times f of t dt over a range which includes t naught, then obviously this will be everywhere this integrand is 0 except when t equals t naught, because at that time delta t minus t naught exists. So, at that time f t naught, which is a constant, delta t minus t naught is delta function is being integrated, therefore, this will reach f t naught. So, this will yield f t naught, that is how it goes. In other words, if you multiply f of t delta t naught, this is after all f of t naught delta t minus t naught, and you integrate f of t naught delta t minus t naught dt. Whenever you integrate through a delta, the value increases by 1 unit, and that 1 unit multiplied by f of t naught leads this result. So, this can be put in this fashion. Whenever you integrate through a delta at a particular point, whatever, if suppose you have some kind of curve like this which includes a delta function, if you integrate that at this point, because of delta it jumps by 1 unit because of the delta function. To summarize, we had in this course of this lecture reviewed the concept of complex frequency signal and identified the complex frequency components present in some example signals which we have taken up, and then later on we introduce ourselves to the 3 singularity functions which play a very important role in describing functions which are either continuous or have discontinuous, which are either discontinuous by themselves or have discontinuous derivatives. The 3 functions that we have familiarized ourselves with are the unit step function, the unit ramp function, and the unit delta function. All these play a very important role in describing either response variables or excitation variables which are piecewise continuous, but have discontinuities at some point either in themselves or in their derivatives. We will take up some examples involving the use of these functions in our next lecture.